Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh, and very good morning. I hope all of you are doing well today. So for today, we are going to look at the introduction for air breathing engine, and there are a few subtopic under the introduction section, where the first one is open cycle, single shaft and twin shaft arrangements. And then we have the multi-spool arrangements. 1.3 is closed cycles. Then we have aircraft propulsion, industrial applications, and finally, the gas turbine design procedure. So probably by end of today, we would be able to complete all the introduction to air breathing engine. In terms of the learning outcomes, at the end of this session, you should be able to investigate the operating principles and application of air breathing engine, right? Meaning that you would be able to know what's going on, how jet engine or air breathing engine works in terms of the principles and the application. And you should also be able to analyze the open cycle single shaft as well as twin shaft arrangements, and analyze multi-spool arrangements, and finally identify the type of air breathing aircraft propulsion. Oh, there's another one. Discuss gas turbine design procedure. So the topic 1.6 is on the gas turbine design procedure. So these are the learning outcomes that you should be able to grasp or should be able to obtain at the end of this particular session. Let's us look at the background of air breathing engine. So for those who have taken propulsion as the prerequisite for this particular course, you should be able to re-look back at the fundamentals of how propulsion works in terms of the air breathing engine as well as the rocket propulsion. We have known that gas turbine engine has been known to produce satisfactory mechanical power, right? In terms of due to the no reciprocating and rubbing parts resulted in few advantages. The first one is few balancing problems. We know that when you have no rubbing parts, you do not have reciprocating parts that in terms of frictions, right? So you will end up to have less balancing problems. And at the same time, you will also have low lubricating oil consumption and high reliability. So we know that gas turbine engine, it is of course expensive, but you can rely on it. It has a very high reliability. In terms of the main components, as I mentioned last week, air breathing engine would have three main components. The first one is the compressor, and then the combustion chamber, as well as the turbine. Remember that we are not going to focus in this particular subject in terms of the inlet as well as the nozzle part of the air breathing engine. So this is shown in figure 1.1, which is given here, where this is just a simple schematic flow of gas turbine system. I believe all of you have seen this in the propulsion subject, where the symbol or the icon being used for compressor, right? You have a large area intake, and then it has the outlet for the compressor is smaller than the inlet where the air being compressed, okay, and then this is where the air will flow into the combustion chamber, where we feed in fuel and combustion will take place, and then the air will be supplied to the turbine section. As you can see that the symbol for compressor and turbine is the other way around, where it is being flipped where turbine has a smaller inlet and a larger outlet. Okay, the air being expanded in the turbine that can produce power output. So this particular simple gas turbine system is shown in this figure 1.1. So in practice, losses occur in both the compressor as well as the turbine, which increases the power absorbed by the compressor and decrease the power output of the turbine. Right, the two main factors normally affecting the performance of gas turbine engine can be, namely, the first one, the component efficiencies. Component meaning that the compressor, the combustion chamber, and finally the turbine. So those three major components efficiencies will bring effect to the performance of the gas turbine engine. And the other one is turbine working temperature. So what we call it as the turbine inlet temperature, TIT. And the higher the turbine inlet temperature coming out from the combustion chamber, you will have a better performance of the gas turbine engine. The overall efficiency of the gas turbine also depends upon the pressure ratio of the compressor. So the development of science, aerodynamics, and metallurgy allows advanced engine using pressure ratio up to 35 to 1. This is at the compressor stages, okay? And the component efficiencies, roughly around 80 to 90%. Probably there are a little bit higher for more modern engine, okay? And turbine inlet temperature of more than 1650 degrees Kelvin. Possible system for combustion, right? We have two possible systems. One is the constant pressure combustion, and the other one is constant volume combustion, right? For constant pressure combustion system, where we will have continuous combustion process, meaning that pressure is being kept constant, we will produce a continuous combustion process. And we know that there are no valve needed in the system for combustion when we opt for constant pressure. Whereas for constant volume, we will use a higher thermal efficiency, right? So because you want to stay constant in terms of the volume, you will have greater mechanical difficulties, right? Because of the mechanism and intermittent combustion, right? So what means that here is that the difficult design that need valves to isolate combustion chamber with the compressor and the turbine. Right. In terms of the additional parts, other compressors and turbines can be added, right? In terms of those three major components, the compressor, combustion chamber, as well as the turbine. So you can also add other additional parts. For example, like intercooler between the compressors, as well as reheat combustion chambers between the turbine. So for many reasons, obviously to improve the performance of the gas turbine engine, right? A heat exchanger can also be introduced, right? And in these refinements may increase the power output. Whenever you want to add additional parts, obviously the ultimate aim is to increase the power output and efficiency due to the expense of added complexity. So whenever you add more parts, you will add more complexity to the engine, meaning that it will also increase the weight of the overall engine, as well as the cost in terms of producing it, at the same time to maintain it, right? There are two types of system for off-cycle. One is called open cycle, the other one is closed cycle. This is just a revision for all of you. For the open cycle system, we know that fresh atmospheric air is drawn into the circuit continuously. For example, like the gas turbine engine on an aircraft, right? So you have a continuous air, which is atmospheric, right? It is coming from outside, being drawn into the inlet, going into the compressor, and then so on, right? Where energy is added by combustion of fuel. So you add fuel, you do perform combustion, and you will the air will gain energy from it. Okay, and then product of combustion is expanded through the turbine, and it will flow into the atmosphere back, right? That is what we call the open cycle. So one way in and one way out to the atmosphere back, right? For in terms of the closed cycle, right, the same working fluid is circulated, meaning that whatever comes in, it will be going out through the system and being feedback into the system. And fuel cannot be burned in the working fluid because you are going to use the air or the gases again in terms of in the system. So energy must be added in the heater separately. So you need extra compartment or additional parts. And then the combustion gases do not pass through the turbine because the system, the heater, it is separate. It is not, there is no combustion occur in the working fluid. Okay, those are the two differences. Okay, the differences between an open cycle and closed cycle. So you may be able to now compare the performance of the two systems. Let us look at this simple closed cycle system. Just now, figure 1.1, we have looked at the open cycle, right? And this picture or the schematic diagram shown the simple closed cycle, where we have the air coming from the pre-cooler. Okay, let's say it started before going into the compressor, and the air the gases being heated, right? It is you need external heater, right? And then going into the turbine and being passed back into the pre-cooler to prepare it, because everything goes out from the turbine is slightly hotter, and then you have to chill it back before you supply it back to the compressor, and then the process continues.